The biggest shift here is that post-training is starting to behave like a design space, not just a final polished step. One line of work shows you can convert a Qwen 3 style autoregressive model into a diffusion language model with surprisingly little compute, while another shows why long context retrieval breaks when the context gets denser, not just longer. And underneath both is the same theme. The geometry of training matters as much as the objective itself. Keep watching, because the surprising part is how these models search, compress, and preserve capability under pressure. Let's explore the first paper, Data-Efficient Autoregressive to Diffusion Language Models via On-Policy Distillation. This paper from Texas A&M University introduces OPDLM, a data-efficient way to convert autoregressive language models into mass diffusion language models without full diffusion pre-training. The key idea is on-policy distillation. The student, initialized from a Qwen 3 checkpoint and given bidirectional blockwise attention, generates its own reverse diffusion trajectories, and the frozen original ARLM provides token-level target logits on those same states. This directly addresses two bottlenecks in prior AR to diffusion conversion: knowledge loss from replacing next token training with diffusion training, and the train inference mismatch caused by training on random masks rather than sampler-induced states. On the main 8B setting, OPDLM trains with only 0, 66B tokens and 4.2 times 10, 18 flops, yet remains competitive on benchmarks such as MMLU, GPQA Diamond, AMI, 2.4, and LiveCode Bench, while the full comparison set shows 15 times to 7,000 times fewer training tokens than established DLM baselines like SDAR, Dream, LLADA, and FAST, DLLM v2. The method also preserves zero-shot capabilities absent from its training corpus, including extended thinking and multilingual evaluation, and can be specialized for math. OPDLM Math 8B thinking reaches 93.8 on GSM 8K, 92.4 on Math 500, and 50 on AIME 2.4, all without a pre-trained DLM stage or verifier reward. The work reframes ARLM to DLM conversion as post-training rather than pre-training. Let's explore the second paper. Dense contexts are hard contexts. Lexical density limits effective context in LLMs. This paper, by researchers at Politecnico di Torino and the University of Turin, argues that long context failures in open-weight LLMs are not explained by input length and needle position alone. Lexical density, measured with moving average type token ratio, is a third axis that shrinks effective context capacity. Using 3 matched find-the-needle benchmarks width is approximately equal to 1-2K token contexts. The authors show that MK-NIA is sparse at MATTR equals 0.58. Scene rules is denser at 0.75, and word checker is maximally dense at 1, across 8 open LLMs from 9B to 685B parameters. Models that are near perfect on MK-NIA collapse below 60% retrieval on the denser benchmarks. At the deepest positions, average accuracy changes by plus 1% on MK-NIA, 27% on scene rules, and 31% on word checker relative to the 2K token baseline, and within benchmark sparsification recovers performance by up to 24% on scene rules and 30% on word checker. The failure mode is model specific under high density. DeepSeek V3, 2, Llama 4, Maverick, and Mistral Small mostly conflate candidate and query text. GPT OSS models increasingly abstain, and Qwen 3. 5 models often invert the search procedure and truncate, revealing that dense contexts do not just reduce accuracy, but change how models search at all. Let's explore the third paper on the geometry of on-policy distillation. On the geometry of on-policy distillation studies post-training dynamics in Qwen 3 reasoning models and shows that on-policy distillation, or OPD, is neither supervised fine-tuning nor reinforcement learning with verifiable rewards, but a distinct geometry in parameter space. Using BF16, aware sparsity, principal angle rotation, normalized spectral shift, and update mask localization, the paper finds that OPD sits in a relaxed off-principle regime. In the controlled Qwen 3 8B comparison, visible update sparsity is 8.1% for SFT, 51.6% for OPD, and 77.2% for RLVR, while representative principal angles are above 10 degrees for SFT, around 1 degree for OPD, and below 0.5 degrees for RLVR. The authors then show subspace locking. OPD's cumulative updates rapidly collapse into a narrow, low-dimensional channel, and a rank 1/6 projection applied from about 20% of training preserves OPD performance but degrades SFT, indicating that the early subspace is functionally sufficient. Control experiments reveal that token sparsification at 25% or 50% and off-policy rollouts preserve this rank trajectory. But mixing OPD with RLVR changes it, so the critical lever is objective composition rather than runtime sampling. The study is framed around Quen 3 8B with a Quen 3 3.2B teacher on DAPO, Math 1 7K, and it argues for geometry-aware OPD designs that regulate update subspaces instead of only increasing token-level supervision density. That's a wrap on today's AI paper highlights. Thanks for watching.